有了，有了。妈的，大胡子，给他便宜了一个亏。
是那个人家好啊。你今天中午没去啊？
去的。
考证奖那个你去了吗？
So you are going to post the solution, right? Yeah.
你今天我那个，你听到之后我才考。
是后半段才来的。
你哦，那我是走以我走以后来的。
他讲的咋样？
听不懂，听不懂我走。应该是。
So here's what I did. All right, so X and Y. Well, it was one.
下周我们讲，下周咱们讲。
我今天听什么？因为就是从礼拜就是这周一开始讲 SVD， 就是讲第7章的是吧？
我在想，我们到时候为了拖时间，把 SVD 那种从头到尾再 review 一遍。然后再继续讲，这样子时间刚刚好。但是怎么讲？
你不是听了 SVD 吗？他怎么讲？
听
那天
我自己去理解，应该不会难到哪里去。我会把它理解好的，我会在反正礼拜3之前把它理解好。我下周3好早上讲完，下午讲。下周3又是我讲。
他下周3不在的话，你下周3早上讲什么？
讲那个 low rank 的那个。
哦，seminar是吗？又排了你讲，靠一学期讲2次。
很难受。
他不在呀，他不是周3不在吗？
对啊。
那你怎么讲？他不在现场，你怎么讲？
这是我讲啊，他说你去讲就好了。就抱大腿了没了。我其实比较慌的是这边的讲。
这边。
这个是教学生，那个是私立所谓。
你要是会 SVD， 你就讲 SVD 就行。我觉得其他的都不行。
我 SVD 其实我目前没看过，但是我感觉应该不会难到哪去。
上节课我也没听，但是看。
就是我是这样打算的，就是 PCA review 一遍他讲的 ，review 完之后然后讲 PCA， 讲完之后看一个例子就完事儿了，扯了。
可以。我要是我讲最后一部分的话，我还不知道。
我在想，主要他们会问什么问题？
不知道，这届学生水平很高。
但我感觉打保和 PC 很多人不懂。
他们上一节课听得懂吗？
上节课来的人都不太，录像也没有，那不是崩案一样。
哦，上节课他们来的都不多是吗
？SVG 已经崩了，那后面怎么学吗？
他们都没来是吗？我这有10个人，没有。
超少，差不多这样子吧。
好，那就把重新打 SVD 进来。
对嘛？这样就我的意思就是这样拉稀。
反正他们也没有。对，又出现了。
我的茶呢？
你确定你拿来了吗？
高买的。 视力不好。
没关系，我可以坐那边。
是，我真的是视力很差的。
你这边应该空一点。
你这就这个呗。
我想放个屁。
你没近视啊？你都没近视，快近视快！毕业之后就有近视了。自从上了 CS 的课之后，就进得很快哦。
Okay, good afternoon. I think we should start. And thank God, and our camera is back. That means our lecture can continue to be streamed on YouTube. So in the last lecture, we introduced an important decomposition for matrices called singular value decomposition. Singular value decomposition. Abbreviated as SVD. So what is singular value decomposition? So basically it says for an arbitrary n by d matrix, so the number of columns and number of rows are not necessary to be the same. You can always find out a unique set of matrices U, S, and V. But you need to take V transpose. Here U and V are both orthogonal matrices. And U is n by n, and V is d by d. And S is an n by d diagonal matrix. So here, U and V are orthogonal matrices, meaning that U transpose U and UU transpose are both identity matrix. And similarly, VV transpose and V transpose V are both identity matrix. This is called orthogonal matrices. So basically, those equations tells us that the columns of U and the columns of V are orthogonal. Or more accurate, we should say that the columns of U are orthogonal to each other. And also each column is a unit vector. And similarly, the columns V are orthogonal to each other, and also each column is a unit vector. You can obtain the results. We'll assume they are orthogonal vectors. And also S is a diagonal matrix. But here, N and D could be different. So it sounds a little weird when we say S is a diagonal matrix. But it basically says that if N is bigger than D, so this is a layout of S. And diagonal means that on the top D rows, we can form a D by D submatrix. And we say S is diagonal matrix means that all the non-zero elements can only stay on the diagonal of the sub-matrix, sub-D by D matrix. So we can denote the first non-zero elements by sigma 1, and second by sigma 2, and until sigma r. And after sigma r, namely after r elements in this diagonal, the remaining are all zeros. Of course, the bottom part is 0. So those are non-zero elements in S is guaranteed to be positive. Oh, it's not. It's no less than. It's not strictly bigger than. And we call this R non-zero elements in S as singular values. And also, the number of non-zero elements, namely R, is the rank of the matrix A. So R is the rank of A. So further, now that we call the non-zero elements in S as singular values, we can define the columns in U as singular vectors. So we define the columns of U as left singular vectors. And similarly, the columns of V as right singular vectors. So now we can see singular vectors, both left singular vectors and right singular vectors, and also those singular values together consist of this form this singular value decomposition. So this is a definition of singular value decomposition. You can prove that for arbitrary matrix, you have a unique singular value decomposition. And this is just the layout when n is bigger than d for the diagonal matrix, right? So when n is smaller than d, so the shape of S will be like this, because n is small and d is large. And then where does the singular value stay?
In the square part on the left.
Yes, yes, yeah. You can just you put you lay your refrigerator on the ground. You still open the same upper box, the freezing box, right? So still here. You can pick up the first n columns, right? Form a sub-diagonal matrix, a sub matrix, and the singular value can only stay on the diagonal of this submatrix, and also sigma 1, sigma 2 to sigma r. So this is singular value decomposition. And to give some a little bit insight about singular value decomposition, in the last lecture we discussed when we multiply our matrix A with a vector, right? We multiply matrix A with a vector. So A is n by d, and x is d by 1 column vector. You end up with an n by 1 column vector, right? And we're trying to multiply x with its singular value decomposition, and we're looking to the changes of the information when we sequentially update x with v as u. Right? So it is equivalent to multiply x with u as v transpose x. And according to our analysis, when we do the first multiplication, when we multiply x with this orthogonal matrix V of V transpose, we actually do not change anything. We do not change the information. We do not stretch or shrink the length of x. We just do some rotation. We end up with a new vector C. But when we multiply this diagonal matrix S with C, things got changed. Because S is a diagonal matrix, right? So when you multiply S with this new vector, you can imagine that you actually multiply each singular value to each element in C. You either amplify your elements in C or shrink the value in your C. That means that you change the length, of course, and also the direction of C. So in the second step, when you multiply S, actually things got changed. Your information is changed, and you get eta. And in the last step, when you multiply eta with U, because U is again an orthogonal matrix. So when you multiply U again, you actually do another rotation. You do not change the information. So the sole step that melt the information of X and A is only in the second step. Right? When you multiply this diagonal matrix with the vector.
So U is a set of column unit vector, right?
Yes.
And similar to V, why we transpose V but not transpose U?
You can transpose U, whatever. If you do U transpose, it's still a column. It's still a column matrix. That's just a tradition. That's just tradition. You can write USB. If you like, you can define things like that. Because U and V are both full orthogonal matrix, so their transpose is orthogonal matrix as well.
Okay, so no matter if we transpose it, we'll get the same result.
What do you mean by same results?
Like USV or USV transpose.
Yeah, that means if you define your singular value decomposition like it's to be USV rather than USV transpose, you still get this, right? But these two forms are equivalent in that when you do the transpose of your result here, you end up with the traditional definition. It's just your habit. Okay, you can define according to your own preference. But this is just a traditional definition. Any other questions regarding to the definition of SVD? Okay, great. So at the end of last lecture, I was planning to show you how to write one line code to implement SVD, but unfortunately, due to the problem, we were not able to make it. So I want to supplement this. Because in your following homework, your next homework, you will be asked to do some single value decomposition or eigen decomposition. So I guess my example will help you better with the homework. So here, so does everybody see it clearly? Do I need to enlarge the text? Okay. So here's one instance. So which can explain the procedure we discussed before, right? A moment ago. So let's assume our So suppose our matrix A is kind of a 4 by 2 matrix. So N is 4 and D is 2. And we can run, of course, we can run SVD to get our decomposition. And here is the U matrix and V matrix. So you can see U is and 4 by 4 orthogonal matrix, where each column is a left singular vector. And V is a 2 by 2 orthogonal matrix. And S is a 4 by 2 diagonal matrix. And we can say, what does it mean for diagonal matrix? So we can see the singular value stays on the diagonal of the top 2 by 2 submatrix. So now, when we multiply A with a vector, and here, for illustration, we assume that we multiply A with a unit vector. So this unit vector X comes from normalizing this vector. So this vector is not a unit vector, but we can normalize this vector by dividing its Euclidean norm. We get a unit vector of x. So because x is a unit vector, then x must stay in this unit 1 circle, right? In a circle with radius 1. And also, we know that V is orthogonal matrix. So meaning that each column of V, namely each right singular vector, is a unit vector. So V1 and V2, namely the first column and the second column V, are both staying on the circle, on this unit 1 circle. Because V1 and V2 are orthogonal, so we can say here's V1, here's V2, right? And our first step is to multiply x with V. So multiplying x with an orthogonal matrix actually does not change the length. We just do some rotation. So after the multiplication, the result vector per se will still stay in this circle, right? This unit 1 circle. So this is the first step. The second step, we're gonna multiply per se with the diagonal matrix x. As we just mentioned, in this step, we're changing the information, right? Because you can imagine you are gonna multiply this single value, the first single value of 8.1655 with the first element of C, and second single value of 2.3074, which is multiplied to the second element of C. So actually you amplify the elements in C. Of course, for the remaining values in S, you just extend C by adding more zeros. So here is the result, eta. And here we just threw out those extra zeros in the multiplication with S. So that eta is only shown in the two-dimensional space. But we can say, because of the multiplication with the single values, the position of eta has changed a lot. It is far away from the unit 1 circle. And finally, when we get eta, you multiply eta with u. It is actually another notation, because u is a orthogonal matrix again. And this result is actually a multiplied with x. So, this is a kind of a graphical illustration of the projection length when we multiply arbitrary matrix with a vector. So you can implement this procedure by writing a few lines of code. Very straightforward. So is it clear to everybody, right? So first, if you want to use SVD, we need to import the SciPy library and NumPy library as you roll. And then SVD is included in the linear algorithm sub-library in the SciPy package. So we can, from SciPy package, import this sub-library linear algorithm, and then we will rename it as L8 for simplicity. And here is the definition of the A matrix, as we just showed. And then to call SVD, to get SVD, we can just call SVD. The function is the same name as SVD, and the input is A. And when you call this function, it will return three matrices: U, X, and V, and V transpose. So U, as the name suggests, U, X, singular values, and VT is transpose of V. So we can run this line of code, and we can take a look at the result of U. So this is the result of U, and you can compare it with what we have shown in the cost material. They are actually the same. And we can also print out the singular values. So the return value from SVD function for S, it only contains the singular values. It does not contain the diagonal matrix. So if you want to construct the diagonal matrix, you need to call an actual function, which we'll show later. And also, if you want to show the V, because it returns the transpose V. So if you want to recover V, you need to do the transpose to its transpose again. So you need to print out the transpose VT. So this is V. So this is V. So now, if we want to multiply the original matrix A with a vector x, right? So here is a normalized unit vector x. So as we mentioned, right, we want to normalize this vector to obtain unit vector x, and we can use the two lines of code to do that. And then we first multiply x with V transpose, and to obtain the first vector C. So now we can see this is C. The C stays in the position shown here, but obviously the drawing of the constituent is wrong to the third part of the xy axis because both coordinates are negative, but it doesn't matter, just for illustration. And then in the second step, we want to multiply C with the diagonal matrix X, right? So previously, we just mentioned that the SVD function only returns the singular values rather than the full diagonal matrix. So now if you want to multiply C with the full diagonal matrix, you need to reconstruct the diagonal matrix. So we can call this function. It's called diag SVD. Very convenient. So the input is S and also the shape of your matrix. So we know A is a 4×2 matrix, so your shape of diagonal matrix is a 4×2. So just give 4 and 2 here. And when you run it, you recover our diagonal matrix X. And then you can multiply S with C, you got eta. So we can say here's eta. So the first two elements have already been amplified by the two singular values, but the remaining two values are simply 0 because the last two rows of S is 0. And finally, you will multiply eta with U again, right? Because this is U is an orthogonal matrix, so when you multiply eta with U again, it actually doesn't change the information that is contained in eta. Just do the rotation, so you get the final results. So here's Y, and you can verify it by directly multiplying A with X. So now by comparing the two results, you can see they're exactly the same. So I will upload this code after the class. So for your reference for the next homework. So any questions so far? Okay, it's good. Looks pretty straightforward. So let us continue. So we'd like to find out what SVD can tell us about projection. So when we multiply A with a vector X, it will result another vector, right? And what if I want to know the norm of this result vector? So let us consider. Of course, we can do it directly to the matrix multiplication and then take a norm, right? But now let us consider the form of its SVD. So when we multiply A with X, it is equivalent to replace A with its SVD. So it is U as V transpose times X. It is this norm, right? So what's the benefit of this law? We find that here U is a orthogonal matrix. So so here is another vector, right? So when we multiply an arbitrary vector, say T, with an orthogonal matrix U, and then compute its norm, it is equivalent to removing U. That's the benefit. This looks not very straightforward, but it's very easy to show that. So the norm, the square norm of ut is what? Is ut transpose times ut, right? This is the square norm of ut. And then we can do a simple matrix multiplication. So ut, when we multiply and then do the transpose, it is equivalent to say t transpose times u transpose, and then times u times t. So now we can say, because u is orthogonal, so the middle part is simply an identity matrix. It means that we can remove the identity matrix. So now we get t transpose t. So this is a square norm of t, and this is a square norm of ut. So now we can see the convenience. That is, whenever we multiply an orthogonal matrix to a vector, it actually doesn't change the Euclidean norm. So now, by using this property, because U in a SVD decomposition, it is orthogonal. So we can just remove U. The norm doesn't change. So the norm will be S V transpose X. This is our first observation. And second, what if I choose X to be one right singular vector? What will be the norm of AX? Say if I choose X to be VG, namely J column of V. So in our singular value decomposition, V are called right singular vectors, right? So it can be written as V1, V2 to Vd, right? We know that those singular vectors, namely those columns, are orthogonal to each other. Suppose I just pick up J's column, Vg, as X. Then what will be the norm of AX? What will be the norm of AX? We can try to compute, right? We can try to compute. So, according to what we have derived, right? So this is equal to S V transpose Vg, right? So what is V transpose Vg? We should take a look. So from here, we know V is just consists of D columns V1 to Vd, right? So V transpose is the first row is V1 transpose, second row is V2 transpose, continue to Vd transpose. Right? And now, if you want to compute V transpose Vg, we can directly multiply Vg with each of the row, right? So the first element will be V1 transpose Vg. Second, V2 transpose Vg. Continue, Vg transpose Vg. And Vg plus 1 transpose Vg. Continue, Vd transpose Vg. So what does this result mean? An idea? What will be these elements in the result vector? No clue?
Is it just scaling?
What?
Is it just scaling? Or
This one?
Yeah.
Each element, of course, is a scalar, right? This is an inner product. Right? So what's the value of those scalars? K's. The key problem is what is the value of those scalars? Yeah, a lot of zeros, right? Because remember, in the definition of singular value decomposition, each column V are orthogonal to each other, right? V is an orthogonal matrix, meaning that each column, the columns of V are orthogonal to each other. And also each column is a unit vector. So V1 transpose Vg is simply what? 0, right? And for any row other than G, the inner product between the corresponding row and Vg is simply 0, except the J's row, right? Because Vg transpose Vg is 1. So the result will be 0, 0 until the J's element will be 1, and the remaining elements are 0. It's actually full of 0 except the J's element. The J's element will be 1. So this is V transpose Vg. So now the next step is we multiply this diagonal matrix S with V transpose Vg. So we can say, so now S is a diagonal element with and V transpose Vg is full of 0 except G's element is 1. And now we multiply S. What will be the result? What will be the result? We need to think of the layout of S, right? S is n by d diagonal matrix. So here we just assume n is still bigger than d. So the shape of S will be like this, right? This is n by d. So single value only lies on the diagonal in a small submatrix on the top, right? So here is a sigma 1, sigma 2, sigma r plus 1 to sigma d. Of course, sigma r plus 1 to sigma d are all zeros. Right? So now, when we multiply this S with V transpose Vg, right? This is a d by 1, right? This is n by d. So actually, we can partition S into two parts. The first part is the d by d submatrix. The second part is the remaining part, right? This n by d, n minus d by d. Right? So for the first part, when we multiply S, when we multiply the first part of S with this matrix, what do we get? What do we get? What do we get? So we can consider first, we multiply the first d by d submatrix S with this d by 1 vector. So what do we get? We can try to directly do the multiplication, right? So this is a diagonal matrix, right? So sigma 1 multiplied with 0, which is 0, right? sigma 2 multiplied with 0 is 0. And until sigma j. Right? So sigma j, the jth row, will multiply this vector, will end up with sigma j. Because the jth element in V transpose Vj is 1. Right? And then the remaining rows in this submatrix, when it do the multiplication with this vector, are all zeros. So in the first part, D elements in the result, it only contains one possible non-zero element, sigma j. It depends, right? If j is bigger than r, then sigma j is 0 as well, because it is beyond the position of beyond the number of the non-zero elements in S, beyond the number of single values, right? And the remaining part, because the remaining submatrix of S is full of 0, so whenever it multiplies whatever vector, it will result a vector, right? So finally, the remaining part is just 0. So now our result is what? It's just a long vector full of 0, except in the jth element, which is sigma j. The j's are singular value. Right? And also we know that singular value is always of course here we are talking about general singular value, right? If g is less than r, the singular value, it is a singular value which is strictly bigger than 0. Otherwise, sigma g is 0. Right? That means its norm is what? Its norm is what? Yeah, the norm is simply sigma g, right? Because this whole vector only has one possible non-zero elements, which is sigma j, and also sigma j is non-negative. So the norm of this vector can only be sigma j. Any questions at this point? No questions? Okay, good. Yeah, because this is pretty straightforward, and if you still feel unclear, you can verify it manually after the class. So, so our observation is that when we multiply V A with a left a right single vector, the norm will simply be the corresponding singular value. This is our first observation from the SVD decomposition. So now, let us going back to the problem we discussed in the last lecture. So, in the last lecture, we mentioned that for a original vector or point in the d-dimensional space, I want to find a k-dimensional subspace. We call it a k-dimensional subspace. The k-dimensional subspace actually is constructed by k orthogonal bases. Right? If you still have impression about what we have discussed in the last lecture, right? So it is determined by k orthogonal basis. Orthogonal basis means that U1 to UK are all unit vectors and they are orthogonal to each other. And all the vectors in F is simply some linear combination of those k bases. So we can project X onto this k-dimensional subspace. And then we end up with a projected vector. So we denote the projected vector by pi fx, right? So what is the projected vector? What is the projected vector? Anyone still have an impression about? Yeah, we need to use dot product. So actually, it's a natural generalization from the projection vector onto a specific vector, right? So if you project a vector to a subspace, you simply, the projected vector is computed by simply adding the projected vector onto each of those spaces. Right? So you actually sum them together. So sum from 1 to k because we have k bases. And then each summon is a projected vector by projecting x onto the corresponding basis. Right? So the projected vector is simply the inner product between the basis and x. Here and then multiply the vector. And here, let me emphasize again because these are all the vectors. So I put an arrow here. So U1, U2, UK. So this is a projected vector, right? So you simply compute the projected vector onto each of the bases, and you add them together through vector addition. Right? This is a projected vector. So our question is that I want to know the difference between the original vector and the projected vector. And I want their difference, namely, to be as small as possible. Now, how can we measure the difference? We just compute the norm of the difference. To give you an example, for example, if your original space is a three-dimensional space, right? And here is your x. And your subspace is two-dimensional and determines a xy plane. So if you project x onto this xy plane, you end up with a projected vector. Right? So I need to denoted by the x bar. Right? So now you want to compute the difference between this vector and this vector. And they're known. So actually, this is the length of the difference here. And we want to, as we discussed in the last lecture, we want to find out a set of bases such that this length is small as possible. So now the question is that how can we measure this difference? How can we measure this difference? So directly using the definition here is not easy, right? It's simply you subtract a vector by a linear combination of another set of vectors. It's not straightforward. So if just substitute this projected vector by this summation, right? It doesn't give you much information. So now let us try to find out a deeper understanding about this difference. So we'll begin with the definition of subspace. So the subspace is determined by k orthogonal bases. But you can imagine, if I can extend this k orthogonal basis to a d orthogonal basis, namely we add d minus k orthogonal basis. That is denoted by uk plus 1 to ud. And what do we get? An idea? So this is our k orthogonal basis which determine our k-dimensional subspace, right? So now, if I want to further extend this k basis by adding extra d minus k orthogonal basis, meaning that those extra d minus k bases are orthogonal to each other as well as orthogonal to this k basis, and they are all unit vectors. by using this total in total D orthogonal basis, what can we get?
0.
What?
0.
0. Of course, we can get 0. Even using this K orthogonal basis, we can get 0, right? Because when we set the coefficients for each orthogonal basis as 0, we do the linear combination, we got 0, right? But the problem is that when we supplement the K basis with extra D minus K basis, we have a larger set of bases. With this larger set of bases, what can we get?
It's the original space, right?
Yeah, exactly. Right. We recover the original. If we add them together, we can recover the original D-dimensional input space. And remember, for a D-dimensional input space, every point can be represented as a linear combination of D orthogonal basis. Right? So right now, if we only use a K orthogonal basis, we can only recover a portion of that. That's why it's called subspace. It only contains a subset of the points in the D-dimensional space. That's why it's called subspace. Right? So now if we can supplement those K bases by D minus K orthogonal basis, so that means we have a comprehensive basis. Then we can recover any point in the D-dimensional space. So now let us imagine that although we haven't known which subset of basis we should supplement, we should add into it. Assume we have those extra bases in hand. Then we can use those D bases together to represent X. Right? That means X can be written as a linear combination of those D bases, including both the K basis and the extra D minus K basis. Right? So which is alpha 1, U1, alpha 2, U2, alpha D, UD. Right? The problem is how can we identify alpha 1 to alpha D? Actually, we reviewed this problem in our previous lectures. So how to compute the coefficient? Anyone has an impression on that? Regression? No, it actually has nothing to do with regression. We just need to use our linear algebra knowledge. So basically, you will find H alpha J is simply the inner product between the basis UG and X. That's it. And you can verify it. It's simply verified by what? You can simply multiply both sides by U1. You can do the inner product. So in the left hand side, if you multiply, if you do the inner product between U1 and X, and on the right hand side, we know the inner product between U1 and U1 is just 1. Right? So it is alpha 1. And the inner product between U2 and U1 is what? 0, because they are orthogonal to each other, right? And inner product between U3 and U1, 0. So the remaining inner products are all zeros. So now we can say alpha 1 is the inner product between U1 and X. And similarly, you can obtain, when you multiply both sides by U2, you can obtain the inner product between U2 and X is alpha 2. Right? So finally, as long as we have a comprehensive basis which could recover the whole D-dimensional space, we can express X as again here, right? A linear combination of the whole D basis, where each summon is simply the inner product between each basis and X and times G. So now let us compare the two vectors. Right? One is our original vector, one is our projected vector. So now what can we find? What can we find? We can find the only difference is the number of summons, right? So the first k summons for both vectors are exactly the same. The only difference in X is that it has extra D minus k summons. Right? So now we can say, when we subtract X with the projected vector, the result is simply the summation from summation from k plus 1 to D. And then the inner product between X, between the corresponding basis and X, and times UG. So now from this result, we can get a little bit insight, right? You can imagine this is a basis which determines F, right? Given our subspace F. And we can imagine this D minus K basis determines another subspace F bar. We can, in some sense, we can say, okay, F and F bar are complementary to each other because their bases are complementary. So actually, the difference between X and projected vector onto F is what? It's actually the projected vector X onto a F bar, right? It's actually projected vector of X onto a F bar, the complementary subspace, which is only determined by this D minus K basis. So this is our discovery. So any question at this point? Okay, so great. So going back to our original problem, suppose we have a matrix A. So n by d matrix A, which consists of n d-dimensional vectors. So each row is a d-dimensional vector, right? So in the last lecture, we want to find out the basis such that for each vector, when it is projected onto the subspace F, the difference is as small as possible. And then we come out SSE. Right? If you still have impression, our SSE is just the summation over the n rows of A. And each summon is just the square norm of difference between the ith vector AI and its projected vector. So we want to find out the minimum value for this result, for this SSE, right? This is actually another SSE. So now, by applying what we have derived so far, right? So we can simply take a look. So this square norm is simply a summation, right? Here. Square norm of summation, which is a summation from k plus 1 which starting from the basis supplementary to the k basis here. So starting from uk plus 1 to ud onto d, and ug ai. So here let me put arrow on ai as well. Right? UG. Just here, right? Well, we arrive at this just by substituting this into the SSE. So the square norm of this summation is actually very simple because each UG is a unit vector. So we will compute the square norm. We must come out the cross term, right? Because in the cross term, different UGs are orthogonal to each other. So the cross terms are all zeros. So the only living things are the square of each terms inside the summation. So this is simply the summation of the square of the inner product. That's it. And now if we can simply switch the order of summation. So we put the index of basis outside and put the number of put the index of the vectors, the rows of A inside. So we get I starting from 1 to n and g I squared. Now we can take a look at the inside summation. What does it mean? So what does this mean? What does this mean? Imagine it to be a matrix vector product, right? So this is actually a norm, square norm of what? Of a vector. So the first element will be UG in the product in UG A1. And secondly, UG in the product between UG A2. And the last term is UG AN. It's actually, this summation is actually the square norm of this vector. And what does this vector mean? Can you represent this vector as a matrix vector operation? Come on, we can try it. We can try to do that, right? So here is A, right? Here is A. So what's this vector? How can we come out this vector? Actually, we can decode this vector as the production between A and what? A and UG, right? A and UG. Because when we multiply A with UG, what's the result? We just do the inner product in A1 and UG, the first element, second inner product between A2 and the UG, second element, and continue until last element, the inner product between A and the UG. That is vector here, right? So now we can see actually in this inner summation, it actually is the square norm of A multiplied with UG. Okay. So we know that now the error, the SSE, is simply the summation from k plus 1 to d and the square norm of A times UG. And each UG is in the complementary set of bases. Right? So now actually we have made a big progress in understanding our projection error problems, right? How to reduce the SSE into another projection problem. So, of course, at this point, you can try to use some optimization procedure to do that. But here, I want to analyze a special case. What if I want to pick up? So here's F, right? I want to pick up F from the basis determined by V. V is from our SVD decomposition. So remember, according to SVD, V is a D by D orthogonal matrix, right? So each column of V, the columns of V form a D basis, meaning that if we use columns of V, we can recover arbitrary input vector or point in the D-dimensional space. So now, what if I want to choose F, namely the K basis, out from the columns V, to minimize this SSE? Then, what basis should we choose? So considering a special case, let me repeat again. We'll consider a special case. Now, assume that we know the range of the basis we want to choose. Right? We know, okay, there is a D basis which can determine the whole R to the D space, right? And I want to pick up a K basis to form our subspace F to make our SSE to be as small as possible. And this whole comprehensive basis are from our right singular vectors, V1 to Vd. So then how do we pick up K basis out of those D vectors to make our SSE to be small, to be minimal?
Should you pick the first K because that would give you the first K? Because so the first K, the smaller K is the smaller the singular value, or the bigger the singular value is at that point, right? So you want to pick the first ones because they convey more significant information. I don't know.
You have a very good intuition, right? You should pick up the first V1 to Vk, the first K right singular vectors. The reason is why? Because as we just mentioned, right, when we multiply A with any right singular vector, say the J singular vector, the norm will be sigma J. Right? So our SSE is what? It's here, right? That is when we pick up the K singular vectors in the remaining singular vectors, we compute the norm, square norm of A multiplied with the singular vector and and the summation, right? So the best way is to pick up to choose those singular vectors which correspond to the largest singular values, and then in the remaining singular vectors, its corresponding square norm is the smallest. Any question at this point? Because I want this summation to be as small as possible. To do that, I need to pick up the K basis, K singular vectors, which has the largest results. That is the norm of the A multiplying the singular vectors, right? Only excluding those biggest singular values, the remaining summation will be the smallest, right? So in this case, we must choose V1 to Vk to form F. Namely, the first K columns of the V to form F. Then in the remaining The remaining is the smallest singular values, right? And the summation of the square norms is simply the square of the corresponding singular values, which are the smallest. If you pick up any other singular values, you leave one of the largest singular value into the summation. Actually, your SSE, your projection area, is not as small as possible. Any questions so far?
So if you pick R, like if you set K to be R, then your error would be 0, right? Because
Yeah, very good. Yeah, you're right. And if your K is smaller than R, then
so that's just saying that like A can be represented fully in less dimensions.
yes, that's correct. Because if you set K equals to R, meaning that your projection actually can represent the original full information. In other words, you can imagine. Why should I? You can imagine your x is here. It is strictly in a xy plane. So although x is still represented by 3-dimensional vector, but equivalently, it can also be represented by a 2-dimensional vector. It's not necessary to use 3-dimensional vector to represent x. You can represent it as a 2-dimensional vector. So you can imagine that if your matrix A, each column vectors, each row vectors are all staying on this xy plane, then what's this reduced dimension? You can simply use a 2-dimensional vector to represent each vector, each row in the A, right? So your reduced matrix B just has n/2 of size. Any other questions? No questions? Okay, good. So a very similar problem is called a best rank K approximation. But the problem setting is a little different. So our matrix n/d, right? In our previous problem, I want to find out a reduced dimensional matrix, say n/k, to approximate A as good as possible. Right? Now I don't put such kind of constraint. I want to find out another n/d matrix, which has the same shape or same size of A, but its rank is only K. So rank of AK is just K. And then I want the difference between this matrix and this low rank matrix is as small as possible. And how to measure the difference? We can use matrix norm. I want to find out AK is such that the two norm between A minus AK and the Frobenius norm between A minus AK to the beta norm. So this is a question. This is often very common used problem I want to solve. So from the original n/d matrix, I want to find out the same size but with lower rank matrix AK, such that the two norm between their difference, as well as the Frobenius norm between their difference, are the smallest. And how do we find out? The K is still in a SVD, singular value decomposition. So we can construct the optimal AK by simply using the singular value decomposition. So we can first do the singular value decomposition over A. We get U as and V transpose, right? And so here's U. So let me still assume N is bigger than D. So S is like a refrigerator. And here is D by D. So here is U as and V transpose. So to get AK is very trivial. It's very trivial. So we know that all the singular values are lying on the diagonal in this sum matrix here, right? So here is the sigma 1, sigma 2, sigma r. Now if we want to get AK, we just pick up the first k elements. So just pick up the first k element, sigma k. And then we set the remaining elements on this diagonal to be 0. And then we get SK. We get SK. We can see this is kind of truncation, right? We truncate the singular values at k's position. Namely, we set sigma k plus 1 until the remaining elements is diagonal to be 0. We get sigma sk. Then we multiply U and V transpose again. We get AK. That's it. And you can guarantee that by using this way to construct AK, the Frobenius norm and the two norms between their difference are the minimum. And the proof for this is not very trivial. It's kind of tedious. It's called Eckert-Young theorem, and you can check it out in Wikipedia. But it's not very hard. But it's kind of tedious. So basically, AK can be written as U ASCII and V transpose. And ASCII is a truncated diagonal matrix by setting the first, by only preserving the first k singular values. But of course, you can, to see the computation, we know that in the truncated diagonal matrix, the only first k elements could be non-zero. Remember, if k is large, the k could be, the sigma k could be 0 as well. But it doesn't matter. Let us just assume k is small than r. So that means this part are all 0, and also this part are all 0. So this k columns are possible non-zero, but d minus k columns are 0, and also this k rows are possible non-zero, and the remaining n minus k rows are possible are full zeros. And that means when you multiply SK with the original V transpose, it's kind of a waste because some rows of V transpose actually has no effect, right? So to avoid those meaningless computation, you can just remove the corresponding rows in the V transpose. So we call it VK. When you remove it's actually you should remove the d minus k, last d minus k rows in V transpose. It corresponds to remove the last d minus k columns in V, because this is V transpose. And similarly, because for SK, the last n minus k rows are 0. So when you multiply U on the left, you actually can remove the last n minus k columns, because this part will multiply this part, will be all 0. So we can denote the shrinked matrix U and V by UK and VK. And then you can construct the AK more compactly by multiplying UK, ASCII, and VK. So this is called a best rank K approximation. So any questions so far? Okay, great. So see you in next month.